Hello, everybody. I'm Romaric from the University of Cape Town, and the title of this presentation is Africa Climate Response to Stratospheric Aerosol Injection Materials. And so, motivation of this work is we already know that stratospheric aerosol injection is one of the proposed uh, approaches to cool down the planet alongside other conventional approaches, mostly reduction of greenhouse gas emissions. And it's also known as the only way to rapidly cool the planet within a certain target, although this comes with a large range of risk. One risk that is of interest for us for us here or for my team is basically the regional disruption in rainfall patterns in many parts of the world, especially the Indian summer monsoon region and also across Africa and the Amazonia, where which could also have significant influence on food risk, food security. So, and also, previous studies assessing the potential of stratospheric aerosol injection or SAI use simulations that use a single material, which is sulfate-based aerosols. And a lot is known about what could be the potential impact of sulfate-based aerosol. However, the sulfate aerosol comes with some other issues. Few of them here are the alteration of the stratospheric chemistry that could have a negative impact on the ozone layer. And also, it could um, potentially further the increase of Arctic ozone depletion and even delay the Antarctic ozone hole recovery by over half a century. And and another very important potential impact of sulfate aerosols is the multiple health impact it could have on people, um, uh, as it could increase atmospheric particulate matters um, and induce premature death, and it could have adverse health conditions due to exposure to surface ozone, and also the risk of having exposure to UV radiations that could increase skin cancer risk and related mortality. So in these conditions, apart from the climate aspect we are interested in, sulfate aerosol also could have some negative implication directly on human and society. So, so this study basically is trying to assess what could be the potential of other material that could be used for stratospheric aerosol geoengineering and see how the climate in Africa will respond to those material. And a special focus, with a special focus on the regional mean climate. And here, when we talk about climate, we are focusing primarily on minimum and maximum temperatures and precipitation. So the focus is on Africa. So this is basically the domain we are focusing on here, extending from 30 degrees west to 65 east and 38 degrees south to 38 degrees north. And we divided the continent into 9 regions, as you could see here on the figure. Those 9 regions, was done based on the IPCC ARC's updated region for Africa. So the data we use is basically monthly gridded data set for minimum and maximum temperatures and precipitation. We analyze also on observation data the climatic research unit graded time series. Basically, we use this as a reference to evaluate the climate model data set from the so-called before model to assess how the model would performs before we dive into the impact of SAI. So the climate model data used uh, is basically an F system model output. Uh, so we have the so-called V4 model that simulated historical and future climate. In the future climate, you have three different experiments. The first two are the scenario MIP, SSP 24.5, which is a midway uh, a scenario, while the SSP 585 is a high emission scenario. And the third scenario is a set of four SAI experiment. We use SSP 58.5 as background with injection of stratospheric aerosol into the equatorial region. So four different materials are considered. Simulation includes four different materials. Um, we have sulphur, alumina, calcite, and diamond. And on the left side, we say basically how the simulations were done, the SAI simulation. It follows the GeoMIP modeling experiment. GeoMIP GC sulfur, which basically use as background SSV5 8.5 with stratospheric injection of sulfur dioxide to bring warming to a level close to the SSP to 4.5, which is a medium range scenario. And the major difference between this data and the GeoMIP GC sulfur is that this simulation started in 2030, while the GeoMIP started in 2020. So the analysis we did involve obviously a model evaluation. So the point here is to assure that the climate model used is capable of capturing the spatial distribution of the climate variables, minimum and maximum temperature and precipitation, and also the seasonal cycle across Africa and its climatic zones. And then we assess the projected changes near the end of the century, 2080, 2099, by comparing the future simulation to historical and also the SAI simulation to the SSP 245, which is kind of the reference we would like to achieve with SAI. But here I will just be presenting this point on the impact on the comparison with the SSP 245. So, and the last point of the simulation is now to compare the different material used and see if there is any of them that perform better or in the same or is the same range of performance like the sulfate material by doing the difference between other materials and the GCs and the sulfur-based experiments. So in terms of the model evaluations, here we have the first row is showing the observation crew data set, and the second, the model, and the third row is showing the difference between model and observation. So we have the annual and also the seasonal spatial distribution of minimum temperature on the left and maximum temperature on the right. So basically what we could say is that the model performed very well in terms of representing the spatial distribution of minimum and maximum temperature. And also, and that's well shown in this spatial the pattern correlation coefficients, which varies between 0.84, which is greater or equal to 0.84 in all cases. But despite that good performance of the model, there are still some biases, cold and warm biases, depending on the region, and also depending on the season. So precipitation was likewise. The model also performed very well in capturing the rainfall pattern across the continent, even across the season, with spatial correlation uh, higher than 0.85. Although we have there is a tendency towards dry biases, the half north, then part of the continent and part of East Africa, while in the Southern African region, the tendency is more towards wet biases. So, and in terms of the seasonal cycle, the model also performed very well by capturing both the seasonal pattern of precipitation across all the climatic zones, and same for minimum and maximum temperature, but despite that, there are still some biases that varies depending on the region and the variable. So in terms of the projected changes, while we compare those simulations to SSP245, what we see is this. The first row here is showing uh, a feature without SAI compared to SSP245. That's basically SSP58.5 minus SSP245. And what we could see is that there's a general warming across the whole continent, except some part of Central Africa and West Africa, where we have uh, a pretty significant cooling. But with the SAI experiment, irrespective of the material used, we have a general cooling across the whole continent, except part of the Mediterranean, Africa, and the Sahel region, which generally depict a slight residual warming. But we also notice here that maximum temperature tends, the impact in terms of the cooling with maximum temperature seems to be more significant it's higher than the minimum temperature. With precipitation, generally what we see is basically that it's not as, the impact is not as linear as what we saw with temperature. And it varies across the continent depending on the zones. However, we could see that in the summer, we could see that all materials tend to induce increased precipitation across part of West Africa, the Sahel region, while over Central Africa and part of Southern Africa, they tend to induce a drying. So, and this is basically the same image, but focusing on the climatic zone. And what we see here is basically that apart from Mediterranean, Africa, and the Sahel, where we have a slight increases in precipitation, we have a slight increase in temperature, which is basically a residual warming, as SAR was not capable of offsetting all the warming under SSP585. We see that all the other climatic zone, minimum and maximum temperature is fully offset beyond necessary over all the other climatic zone, irrespective of the injection material used. And also, but with precipitation, we could see that Central Africa, which was expected to become wetter under SSP5 8.5, will become drier. Same for the Southeast Africa, Southeastern Africa, and why the Sahel and West Africa and Northeast Africa who will experience increase in rainfall in some season, especially the summer seasons. So what happens when we compare the sulfur to the other materials? So basically, this is showing the difference between the other material and sulfate. And what we could see here is that the alumina seems to be the most, the one that cools more, produce more cooling across the continent compared to the GC, the sulfur-based, the sulfur material, basically, by inducing widespread cooling across the whole continent annually, but also across all the seasons. While the diamond seems to be the much compared to the sulfur seems to is the one that looks that could produce the less cooling compared to the sulfur material, basically. So that's what we can keep from this figure, but this applies for both minimum and maximum temperature, while the calcite is in between the two. So for precipitation, we could see that all materials tend to induce more drying compared to sulfur, and although sulfur is already expecting to induce drying over the continent, using alumina, calcite, or diamond instead of sulfur will induce even much more drying, which is not good for a continent that rely on rainfall for agricultural production, and in which agriculture is plays a very important role in the GDP of most countries. So when you look at regionally across all seasons, we also see that that tendency is confirmed here, where we could see that alumina, which is the cyan color indicated here, is the one producing more cooling across all regions and season. Of course, except the Mediterranean, Africa, and the Sahel, where where all material tends to induce more warming compared to the pieces sulfur. But across the other region, the alumina is the most performing in terms of cooling. But when it comes to rainfall, we could see that alumina also is the best material to induce more drying across the continent, as across most climatic zones, it tends to produce the highest decrease in rainfall compared to the sulfur material. So the takeaway home message is that the so-called D4 model shows very good skills in representing the climate over Africa. And it's also across all the climatic zone across the continent. Although there are some substantial biases, the model, we can clearly conclude that the model is very good in reproducing the climate over the continent. Also, we could see that all SAR material has shown certain potential in decreasing temperature over Africa, except over Mediterranean, Africa, and the Sahel region, where there are still some residual warming persist due to the materials, the material to just partially reduce the warming over those two regions. SAI impact on precipitation, however, is regionally diverse and is not as linear as we could see for temperatures variables. However, with Central Africa, which was projected to dry, which was projected to become wetter under SSP 585, could become dry seasonally and annually. from an annual point of view, but also seasonal point of view under all materials. Alumina performs the best in cooling the continent compared to all three other material, and also not just the continent, but also all the climatic zones. But it could also induce more drying across the continent. So, and the last point is that there is need for trade-off in terms of when it comes to making any decision about this type of materials in terms of the cooling that can be achieved and the other impacts like on precipitation, and also in terms of environmental and health risk associated with each material. We have an idea already of uh, that's for sulfur-based material, but alumina, although it shows good cooling, it could also have some negative impact on the environment and human and animal health. And also, it also have not too good impact on precipitation, which is very important climatic variables across in Africa, which is a continent that depends mostly on rainfall for its agricultural production, which is the main economic activities across the continent. So this what I've prepared to present today for this annual meeting. Sorry for not being able to join you in New York this year. Thank you very much for your attention.